Hello everyone, this is Rakib, and here you can see it's a finger, and it's my final year project, which is the 3D printed low cost myoelectric prosthetic hand. There are some key terms like 3D printing, like myoelectric. Here is the myoelectric circuit, which is the EMG circuit, and 3D printing we all know that layer by layer printing, and I have used PLA plastic. If you see, here you can see the 3D printer I have used actually the Printfrite repeater software, and Blender is the open source software, and it's really very much easy to make those 3D printed object using Blender. And you can see the finger. Now after exporting this file to STL or OBJ format, you will get these STL files. Then you have to load. Here is the load button. You have to load these files here to this software, which is called Printfrite repeater host. Okay, so after that you can see there are some fingers, connectors, and metacarpal, and some motor mount here. Now what you have to do, you have to connect with the printer by pressing this button, and you have to slice it. Actually, slicing means converting this STL file to G code. Here is the G code, GCO code, you can say that. Now after all these things, after connecting, slicing, and pressing this button, run button, here this 3D printing will be started. Now I can show you a video right now how 3D printing is done. Here you can see a finger is being printed here, and here is the Printfrite repeater host where live action is showing. This is really cool. Like when you are printing this object, these layers are actually graphically visible. Now it takes a lots of time, like 2 hours or 3 hours to print a little finger, but you can actually print any kind of shape by using 3D printer, and is the advancement of technology. Okay, now I will be describing how this 3D printed prosthetic hand is being operated. Now before operation, I have to describe the build materials. These are actually PLA plastic. There are basically two kinds of plastics available to print a prosthetic hand. One is ABS and another is PLA plastic. PLA is user friendly and does very little health injury or harm to health. So I have used PLA plastic instead of ABS. ABS is little bit stronger, but using PLA it just does your work. Now here is a servo motor to move this finger in this direction, and there are actually 5 DC motors, 1 2 3 4 5. These are the motor mounts. Now if I compare this prosthetic hand with a normal hand, you can see a normal hand has this part is called phalanges. Now, and here is metacarpal. There are actually 27 degrees of freedom of prosthetic hand of a normal human hand, but this prosthetic hand actually has only 16. Now coming to the circuitry, here is the circuit. You can see here is the 5-volt regulator, and here if I connect this, I have given a predetermined value to the servo motor, and here is the Bluetooth module. Now I have been doing some research on Android app development, and by using MIT App Inventor I have developed an app, but I cannot show you this app right now because I am describing this video with my Android phone. So I can show you a video how this hand operates by using this Android app. Now here is the video. You can see connecting to the Bluetooth module. Yes, connected, and here is the hand in action. Now grabbing different kinds of objects, and the hand can hold very strongly. I can say that the motors are very much powerful. They are very high torque but very low RPM motors. You can see different kinds of objects here, and the hand is operating very close to the human hand, very close to a normal human hand. You can see another object. Now making something using 3D printing needs lots of patience, and I can say it's really hard to work with 3D printers. You can see an apple, and this 3D printer prosthetic hand actually is ready to be used by any kinds of amputees, upper limb amputees of course. Here is a bottle. Now you can see the hand itself in action without any object, and the tendons which I have used to, here you can see a hand is being held by this prosthetic hand. Okay, now coming to the circuitry again, you can see there are some sensors here. This is the pressure sensor, and I have used a graphical view by using LEDs instead of using LCD monitors or anything else, because using LEDs are really very much helpful to the amputees, because these are graphical and you can see them in action. Now if I press this pressure sensor a little bit, you can see when I am giving pressure, one after one LED is getting power, and after a high pressure, this buzzer will indicate the pressure is very high. So this operation is very helpful to hold soft objects like a baby, hand of a baby, or hand of a very little kids. We just cannot give harm to these little kids hands because they are very soft. So when I will be giving this EMG signal, you can I'll be describing this EMG circuit a little bit later, but what actually these are EMG electrodes. These electrodes are going to be placed to the hand of an amputee, and this is the EMG circuit. Now coming to the moisture sensor. Moisture sensor actually detects the moisture, any moisture. Here you can see a little water here, and it's the same indicator. I have used the same indicator to reduce the place requirement. And here you can see it's the band sensor. I have not used this in this active circuit because I don't need a band sensor to operate this one, and I have given a predetermined value to the servo motor, and is very handy. Now coming to the main circuitry, Here are actually three L290 3D motor driver IC. One L290 3D can operate or can run two DC motors individually. So to run 5 DC motors, I'll be needing actually 3 of them. And if I come to this IC, it's ATmega 328P, which is an Arduino Uno environment, of course. Here is another Arduino Uno because I have been going out of pins after all these connections. So to run these sensors, I have to use another Arduino Uno or ATmega 328P IC. Now I have to save power, so just removing the power from the circuit. Now here is the EMG circuit. EMG circuit actually based on instrumentation amplifier. Here is an instrumentation amplifier. Now the signal coming from the body, I have to collect signals from the body by using these EMG electrodes. If I open one of them, you can see there are some gels and an electrode. To take signal from the body and amplify them after reducing the noises are actually very much hard. Very much harder. There are noises coming from resistors, there are noises from current noise and voltage noise, so we have to reduce all those noises by filtering, rectification and final stage amplification. You can see there are actually two trimmer resistor here. This trimmer resistor actually used to set the gain of this differential instrumentation amplifier, and this trimmer resistor is used to set the final gain of the final output, which will be given to the analog pin of the microcontroller or Arduino to run these motors. Now what's inside an instrumentation amplifier and why we need this kind of instrumentation amplifier instead of using any amplifier. Now instrumentation amplifiers are specially designed and they have very high CMRR or common mode rejection ratio is very important. When you are going very high CMRR and other noise reduction, then you have to consider the price. And basically normally the ranges of CMRR in a normal amplifier circuit ranges from 50 dB ranges from very low like 80 dB, 70 dB, 60 dB, 50 dB. And as we know there are two rails, one is two input rails, and the signal coming from this differential input are very low. So if the common mode rejection ratio is not high, then this signal will be distorted and signal will be lost. So here is the inside view of the instrumentation amplifier. I have drawn it in here. Here you can see is the negative minus V in, here is the positive V in. This is the most important part, R gain, or here is the R gain or trimmer resistor. You have to calculate this gain, how much gain you are going to give to this instrumentation amplifier. Now I have given this output from this instrumentation amplifier is 100, gain of 100. So I have to give this RG value of RG as 470 ohm. This is very important. And after I have found this gain, after that I have to filter out the signal. Here is the high pass filter. High pass filter actually is a high pass filter, but AC coupling is done. We know that AC coupling using as AC coupling circuit operates as a high pass filter. After high pass filter, here is the rectification part. Now rectification is very important because we are dealing with human body. Now we are not supposed to give some input to the human body, but we are getting some input from the human body. So we should be very much careful about this amplification process, because this amplification is very high, and we have to consider some kind of precaution, like the isolation is very important in this kind of circuits. There are optical isolators, there are capacitive isolators. So I have used just rectifiers here to isolate the circuit. And another here is the low pass filtering process. After low pass filtering, I am actually using this streamer resistor to get the final stage amplification, and from this point I am giving this input to the analog pin of the microcontroller. Now here is the main circuitry. Now how this process is done, how these EMG electrodes are actually getting something from the human body. Now to demonstrate this, I have to describe a little circuit here. Actually, when this capacitive and resistive network is being constructed inside the skin, there are actually various layers of skin, like the epidermis, dermis, and inside this skin, inside this epidermis, and between dermis and epidermis, this kind of resistive and capacitive network is being created. And when we flex or extension is done, when a flexation or extension is done, this capacitive and resistive values are changed. When these values are changed, the differential input to this instrumentation amplifier also changes, so the gain also changes. So this is the basic principle of these EMG electrodes. Now coming to the microcontroller input, when I am getting an analog value and it ranges from 0 to 1023, or any value higher than 1023, maybe higher than 1023, and but Arduino can read 0 to 1023. So I have to make a code which has a limitation of 0 to 1023. Now here is the final code I am showing you. There are lots of integer value I have to define, because there are enable pins, there are input pins, and lots of pins here. So after all this defining as output, now when state is 1, this operation is done. When state is 2, this operation is done. When state is 3, all these motors will get nothing, and the motor will stop rotating. Here is the basic code, but you can, and here is the sensor. Here is the code for the sensors. It's a very long code, because there are lots of sensors, like the band sensor, pressure sensor, moisture sensor, temperature sensor. I have been using LM35 for a long time as temperature sensor, but HSM20G is another digital temperature plus humidity sensor. This is just an humidity sensor. Okay, this is not a temperature sensor, but HSM20G works as both. Now this is the sensor code. Now here is the servo angle, predetermined value 110. Now coming to this pressure sensor, and after pressure sensor, here is the humidity sensor code started, and after all that you will see the temperature sensor code. So I can show you how the EMG prosthetic hand or EMG circuit is being operated. Here is the EMG circuit. You can see when I am flexing my muscle, the motors are rotating in one direction, and when I am making an extension of my muscle, the motors are rotating in another direction. Here is a delay. The code is a mess actually. Because of this, you can see there is a delay of this input. Here, now if I show you, the analog values are actually changing here. When I am when I am flexing my muscle, you can see a peak or analog value is changing from a and here is the action of the prosthetic hand.